All right, so no quote of the day today since I was off sick on Monday, so I used the Monday quote for Tuesday's class and then used that for Wednesday's classes. Um, so we'll just jump right into it. Today the plan is to finish up chapter 3 by talking about section 3.6, solving applications with linear inequalities, and then to just do a little bit of practice from some of the previous chapter 3 material. So just take a few problems basically pulled right from the lectures or the worksheets in those previous few sections in chapter 3, but they're a little jumbled up. Can you figure out out of context without knowing what section it's in, what the right tool for the job is, so to speak? Sometimes that's kind of half the battle for some of these application problems is deciding, okay, I know that when I have this type of a problem, I have, these certain tools in my toolbox to use. And when I have this other type of problem, I have these other tools. Sometimes half the battle is just figuring out what type of problem you have. So what tool set is going to work best. Let me change the font color here. So that's the idea of the practice, is just to review the chapter 3 material kind of as a whole and see if we can go one step further and say, okay, can I decide what tools to use for the job and then actually apply those tools appropriately? Let me change one thing here with my OneNote really quickly. Okay, there we go. I think we should be good now. All right, so that's the idea of the practice. And let's get started on 3.6, solving applications with linear inequalities. So we've done several sections now solving applications that are in some way related to a linear equation. With the linear inequality, it's going to be somewhat of a similar feel. We're going to have two mathematical expressions that we're going to have to pull out of typically a word problem that's going to have some context. And they're going to be related to one another, but instead of being equal to one another, they're going to be, one is maybe less than another, one is no bigger than another, something like that. So we're looking for a slightly different set of Q words here. Okay, so let's look at this first example. So here, Johnny sells kitchen aprons online for $24.50 each. How many aprons must she sell next month if she wants to earn at least $1,000? So we know that the equal sign kind of corresponds to is most of the time. So a lot of the times if we see is in a word problem, that's a clue that might be kind of where the equal sign is, where we're saying one thing is another thing. Those are the two things we're equating, and then we can figure out the mathematical expressions, the phrases, so to speak, that we want to equate to one another. For inequalities, it's the grammar can be a little bit more complicated. We can have things like at least, more than, no less than, or at most, or less than, or no more than, or right. So we have to be a little more careful what these correspond to. So we don't just have one kind of Q word that we're looking for. We have several. So we have to be a little bit more aware of the context and what's going on. But I do see at least, and I do see an idea that she's going to sell some number of aprons. That's going to give her some amount of income, some amount of revenue, I suppose. And she wants that revenue to somehow be compared to $1,000. In a previous section, this might have been wants to earn $1,000 or wants her earnings to be $1,000, and that to be would be the is. But now she wants to earn at least $1,000. So let's look at the two phrases. One phrase that's being related is $1,000. Another is how many aprons she sells. Well, let's let N be the number of aprons she sells, and we know that she makes $24.50 per apron. Now, again, in a previous section, I might have just put an equals here and then solved my equation, but I want the earnings to be at least $1,000. So if the earnings are like $1,050, that satisfies it. It's at least $1,000. But if the earnings are exactly $1,000, that also satisfies it. 1,000 is at least 1,000, right? So this would be a non-strict inequality. Again, we just have to be a little more careful with the vocabulary and, just check these edge cases and just ask yourself, based on the phrasing of the problem, does a strict equality actually satisfy the statement? So if she earns exactly $1,000, did she earn at least $1,000? Yes. If this had instead said more than, if she earns $1,000 on the nose, did she earn more than $1,000? Well, in that case, no, right? So if it said more than instead of at least, we would write a strict greater than. But because it says at least, we write greater than or equal to. So that's the difficult first part, right? Getting the information from the problem statement into some kind of mathematical equation, or in this case, inequality. Once we're in this format, though, well, we're back in chapter 2. We're pretty familiar with these next steps. We isolate the variable term. Well, nicely enough, the variable term is already isolated from the constant term, so no additional work to do there. We isolate the variable. We do that by dividing by the coefficient of the variable. And I keep writing 24.50 just because I'm thinking in dollars and cents, but you could write 24.5, that's fine. And let me come over to my calculator. I have a feeling we'll be using the calculator a little more this session, so I think I will actually switch my share to include it. There we go. And I see that N bigger than or equal to, note that 24.50 is positive. I do not need to switch the sign. So that's one little additional detail I need to remember anytime I'm dealing with an inequality. If I divide by a negative, or for that matter, multiply by a negative, I need to switch the direction of the inequality, but that doesn't apply here. So I want to figure out what is 1,000 divided by 24.5. And that gives me 40.8 approximately. Now, I suppose I could leave my answer like this, but what are my units? My units are number of aprons, right? It's a little bit silly to say that I have to sell at least 40.8 aprons. I can't really sell 0.8 of an apron, right? I mean, maybe we could really stretch this analogy far and say something like, averaged over 5 months, she would need to sell 40 aprons per month plus an extra 4 aprons over those 5 months or something. But that's not exactly what we were asking, right? What would be the better way to answer this question? How many aprons does she have to sell next month if she wants to earn at least $1,000? Well, she can only sell whole numbers of aprons. She could sell 30 or 40 or 41. If she sells 40 aprons, she sold too few to make $1,000 of revenue. She has to sell at least 41 aprons. So Johnny must sell at least 41 aprons. Right. So in this case, we round up because n has to be bigger than or equal to 40.8. We can't sell a 0.8 of an apron. At least I don't think we can. I don't think we can cut the straps off and charge somebody 80% of the value. So we round up to the next whole number, 41 aprons. Do our units make sense? Well, what were the units of 2450? That was units of dollars. What were the units of n? N is just a counting number. It's the number of aprons she sells that has no units. 1,000 is in units of dollars. And when I divide these, my units of dollars divide out, giving me a counting number, which is what I want. So my number of aprons is 41 or 40.8. The unit does make sense. If I ended up with a unit of dollars or something when I track this through, or even worse, something like dollars squared, I'd be suspicious that I did something wrong. I'd want to go back and check. I also noticed that this is a pretty reasonable answer. I didn't say that she has to sell 20,000 aprons. That wouldn't make sense at all. I didn't say that she has to sell negative 40 aprons. I didn't say that she has to sell, 3 aprons. Those would be examples of answers that we could pretty readily see from the context that that's not right. Obviously you can't sell a negative number of aprons, and just understanding that she makes about 25 bucks an apron and has to make $1,000. She doesn't have to sell 30,000 aprons. She has to sell more than 5 aprons, right? So, but our answer does seem to be reasonable in this context. 40 aprons, that's about 25 bucks an apron. Roughly, that's about $1,000. So that seems about right. So again, some people don't like word problems because admittedly, this first step is a challenging step. But if you kind of flip that on its head and say with word problems, there's so much more context. There are units, there's kind of reasonability, how many aprons does it seem like she ought to sell, that you can use to check your answer or to guide your analysis. That maybe offsets that little bit of extra work getting things into an equation or inequality. Okay, so let's work on this problem. Mona is planning her son's birthday party and has a budget of $221. Maybe I'll actually switch my share back over to OneNote so you can see this a little bigger on your screen if you're on a tablet or phone. Mona's planning her son's birthday party, has a budget of $221. The fund zone charges $17 per child. How many children can she have at the party and stay within her budget? Again, keep in mind that you probably can't have a half of a child or something at the party. So address that in your answer. And then I'll leave the next problem up on the screen if you want to work ahead. So we'll take maybe about 3 minutes to go through this one. Okay, so this problem can be maybe a little bit more challenging than the last one we did. And the reason is that, well, looking through here, I don't see, greater than or less than or more than or less than. So what uh, are my word or words that are describing the relationship between two components? Well, I'm asking how many children can she have at the party and stay within her budget? So I need to even use the context a little more here. She has a budget of $221. What does it mean to stay within a budget? Well, it means that the actual cost, the actual, say, cash outlay, is less than or equal to the budgeted amount. So in this case, stay within is the the pair of words. I was going to say the word, but it's the two words that describe the relation between these two ideas: how much she's actually going to spend and how much she had budgeted to spend. And she needs to invite no more children than she can, such that the amount that she is going to spend uh, has to stay less than the budgeted amount. So what's the budgeted amount? $221. What's the actual incurred cost for inviting N children at a cost of $17 per child, 17N? So I have to have 17N less than or equal to 221, or N less than or equal to 221 over 17. And that gives us exactly 13. So not 13.1 or 13.7 or something, but she can invite up to and including 13 children. So Mona can invite, or I guess I suppose her son can invite, but can invite up to 13 children. In this case, we didn't need to worry about which way to round. We do still have the stipulation that we can't invite a half or a quarter or something of a child, but our answer turned out to be exactly a whole number. So we could invite that 13th child and be right at $221 in cost. And again, just like the last problem, the units check out. Same structure as the last problem. And this is a reasonable answer. I don't have an answer that's like she can invite up to -5 kids, or that she can invite up to 100 kids. That's clearly not correct. This seems like a reasonable answer based on the context. Any questions on this one? Okay, so another example in this section, Kim Yen needs to spend $3,750, or sorry, needs to earn $3,750 per month in order to pay all her expenses. Her job pays her $3,170 per month plus 4% of her total sales. What's the minimum her sales must be, in this case, in full dollars, in order for her to pay all her expenses? Okay, so she needs to earn $3,750 per month, and her job pays her $3,175 plus 4% of her sales. Let's call her sales S. And we want to know the minimum her sales must be in order to pay her expenses. So what does she need? She needs that she needs her income to be greater than or equal to her expenses. That is in order to pay all her expenses. So again, we don't see words like less than or more than or something like that here. We have to use the context a little more thoroughly here. Okay, she needs to pay all of her expenses. She gets a certain income. That income has to be greater than or equal to her expenses. Her expenses are $37.50 per month. And her income, she wants to be greater than or equal to that, which is $31.75 plus 4% of her total sales. That's 0.04 times S. Let me clean up this bit here just a little bit, times S, bigger than or equal to. There we go. Okay, so I have a linear inequality. I have not yet isolated the variable term, so let me do that by subtracting 31.75 from both sides. And 37.50 minus 31.75 gives me 575. So her sales times 0.04 have to be bigger than or equal to 575. And I can now isolate the variable. And I do 575 over 0.04. Whoops. So I just divide 575 by 0.04 on my calculator, and I get 14,375. Let's check our units and make sure all of this makes sense. So 31.75 is in dollars. 37.50 is in dollars. 0.04 is just, it's unitless. It's just a percent of the total sales. So sales should be in dollars to make all this work out. And I see indeed that sales is in dollars. That's what we would expect. And we know that she needs to make something like, well, 3,100 to 3,700 is about $600. She needs to make $600, and that's got to be a pretty small fraction of her total sales. So, say something like 1/20th or so. Does this make sense that she needs to sell about $14,000-15,000 in sales in order to meet that goal? Yeah, that seems like a pretty reasonable number. And here we got exactly 14,375, no decimal points or anything. So we can just stick with this as the answer. And we can say that Kim Woo-yeon has to sell or has to make at least $14,375 in sales in order to meet her monthly expenses. Any questions on this one? Okay, then let's work through this problem. This has a couple extra pieces to it. So maybe we'll take about 4 minutes. We'll work through this problem, and then we'll move on. Okay, it's been about 4 minutes. So this one again has some context. We do see this nice identifier at least, so that gives us a nice clue that we want something to be greater than or equal to $1,500. And we see that she charges $45 for a haircut and style. Her monthly expenses are $660, and she wants to save $1,500 per month. How many cut and styles must she do to save this amount? So one thing about that comes up sometimes in these word problems is there might be more than one way to set up the problem. So in this case, one way to look at it is to say that her profit, in other words, her income, how much she takes in minus her expenses, has to be bigger than or equal to $1,500 so that she's able to save that $1,500. So if on the left side we have income, how much she takes in, that's $45 per haircut times, let's call the number of haircuts she does N. So 45N is her income. Her expenses were given in the problem statement as $660 per month. And she wants this to be greater than or equal to her desired monthly savings of $1,500 a month. So this is one way that we could set up the inequality based off of the problem statement. The first equation or inequality solving step that we would apply here is to isolate the variable term, adding 660 to the other side. We would actually get another inequality. And we could have actually gotten to this inequality directly from the problem statement. Somebody else might have looked at this and said, well, what does she want to do with the money? She wants to do two things with the money that she has: pay her monthly expenses and accumulate a certain amount of savings per month. And how much money does she need to do that? So what would her income be? 45N. And that has to be bigger than or equal to her expenses plus the desired savings. So somebody else looking at it from a different perspective might have taken this approach and jumped right to this inequality. We can have two different inequalities, or maybe there's even a third way to set this up that I'm not thinking of. We could have multiple different ways of translating the problem statement into mathematics, but note that these are equivalent, right? They're mathematically equivalent to one another. So we're still going to get the same answer N, whether we set it up one way or the other, but it's just a question of context and how you favor doing things. So maybe this way makes a little more sense to you. Maybe this way makes a little more sense to you. It's not that one way is right and one way is wrong. It's just different ways of looking at the same problem. But regardless, we get down to the inequality that 45N is bigger than or equal to 660 plus 1,500, or 45N bigger than or equal to 2,160, or N bigger than or equal to 2,160 over 45. And going over to the calculator, this gives me 48. Note that the units on this right-hand side are in dollars, 45 is in dollars, N is a counting number. My units of dollars divide out as I would expect, giving me a counting number for N, a number of haircut and styles of 48. I also note that I don't have any decimals here, any fractional components. So my answer wasn't 48.3 haircuts. My answer was exactly 48. So I can just stick with this answer. I can say that she has to do at least 48 haircut and styles this month in order to both pay her expenses and have the desired savings. If I had an answer like 48.1, then I need to round up to the next one, and she'd need to do 49 haircut and styles at least to cover her expenses and have the desired savings. If we got 48.1 and rounded to say the nearest whole number down to 48, she wouldn't quite have enough to make the 1,500 in savings that she desires. So we have to be, in these context problems, we have to be careful with which direction we round. Often we end up rounding up all the time or end up rounding down all the time or for a given problem statement. Often in these problem statements, it's not so much a question of whether it's something 0.1 or something 0.9 that makes us round one way or the other. Often it's a question of we always round down or we always round up because of the context. Okay. So just, something else to kind of keep in mind as we're, moving into more complex chapters. We're building on previous structures. There's a little more that we have to keep in mind, a little more that we have to think about. But again, I think if we keep tying things back to previously solved problems, and especially in application problems like this, always asking ourselves, does our answer make sense, right? If I had somehow got an answer with units of dollars, how many haircuts does she have to do? $48. Well, no, that's the wrong unit, right? Or is about 48 haircuts, does that seem in line? Yeah, that seems pretty reasonable. If I had 48,000 as the answer, something clearly went awry there. If I had negative 17 haircuts as the answer, something's clearly wrong there. Okay. All right, any questions on anything in this section so far? And as an aside, I think a couple lectures ago, I gave you guys when we were talking about mixtures, I gave you guys an exercise. Yeah, it was this one. Speaking of negative answers, I gave you an exercise to kind of practice at home where we were looking at mixtures of different vinegar solutions with different levels of acidity. And I said, well, I think it's kind of obvious in a sense that if we mix an acid that's 5% or a vinegar that's 5% acid by volume and one that's 7% acid by volume, that we can't somehow mix those and get an 8% by volume acid. We can only get percent acidities between 5 and 7% if we're mixing substances with acidity of 5% and of 7%. But we could plug in 0.08 into our equation where we would otherwise plug in, say, 0.062 or something. Can't we just solve this equation, and won't the mathematical model say something that it ought not say? All right, won't the mathematical model tell us that we will be able to mix this much of solution 1 and this much of solution 2 to somehow get 8% acidity out of 5 and 7%? Well, what we'll have is we'll either have X as negative or Y as negative. Our mathematical model will come up with a solution, but it'll say you have to mix, negative 20 ounces of vinegar 1 and plus 50 ounces of vinegar 2 in order to get the desired acidity. And pretty clearly, we can't practically mix together negative ounces of something with positive ounces of something else. So that's really, so we get a mathematical solution, but clearly that's not a solution in the context of the problem. So again, I assigned that kind of as an exercise for you to work through at home and to think through. And, that just shows the power of always keeping in mind the context. If I had asked, instead of 6.2% here, if I had asked 8%, you would have gotten, you could have written out the equation, you would have gotten numbers for answers, but one of those numbers at least would have been negative, and then it would have, well, exactly one of them would have been negative because they have to add the positive 30. And then, uh, if you just took those answers and ran with them and circled them and said, that's my answer, well, that clearly doesn't fit the context, right? So really that question would have no valid answer because of the context. We can't mix together negative volumes of liquids. So just as kind of an aside to bring that point home from a couple lectures ago. Okay, so any questions on applications with inequalities? All right, then what I'd like to do for the rest of today's class is to go through just some practice. Here I have 4 problems. These problems should look, somewhat familiar. These, well, at least 3 of the problems should look familiar. These are from previous sections. And I wanted you to take a look at these out of context and try to read each problem, decide what set of tools in the toolbox are appropriate to use, what mathematical models, what tools and techniques, what formulas would be applicable in each of the situations, and then work on applying those formulas, getting all of the information out of the problem statement and working to a solution. So we have 4 problems here. These are some of the more challenging problems from each section. Definitely I think the level of difficulty of the different sections is a little bit different at a baseline, but from each section, these are some of the more challenging problems. So this is a good, really assessment of how well you've mastered that material. Now, one of the problems is from this section, so that problem might be a little more challenging for you relative to the difficulty of the section, even because we just introduced it today. But see if you can go through, work through each of these, and we'll probably take about 5 minutes for the first one, come back, talk about it, 5 minutes for the second one, talk about it, somewhere along those lines. But maybe I would recommend first take a couple minutes, go through and see if you can label each one just with maybe what section it's from, what model or formula might be the main one that's going to be used there, and then go through and start solving them. So we'll take about, maybe 5 minutes for that kind of initial step of seeing for each one what section or model or formula would apply, and then solving the first problem with Vern here. And then we'll come back and talk about it for a few minutes. Okay, so let's look at the first problem, the Vern problem. Hopefully you had enough time to go through and label the four problems as well to kind of sort out maybe what set of tools or what set of formulas might apply in each case. So the Vern problem, we see that it's talking about he wants to invest money, he's going to earn interest, he wants to know how much he should invest. This is going to be an application related to money, to finance, using the interest formula, the simple interest formula, I equals PRT. The Rahul problem, if I glance through this, okay, they're going to rent a truck, they have a budget, they need the truck for 2 days. What is the maximum number of full miles they can put on the truck? This sounds like an inequality, that I'll be able to drive the truck less than or equal to some certain number of miles. So I'm going to be thinking of my inequality section here. I'm going to be maybe not targeting an is as my equal sign, but maybe looking for something less than or greater than, or maybe even having to use a little more context to get my answer. In the third problem, we have a ladder that's going to be used to paint a house. The ladder will lean against the house. I'll draw a little diagram over here, but I'll erase it because whenever I start adding spaces, the diagrams don't shift on as well. But we have a house. We have a ladder leaning against the house. The base is a certain distance away from the base of the house. This certainly seems like a right triangle problem, like a geometry problem. And if we know this and this number, we're looking for this number. We have a right triangle. We're looking for one of the side lengths given the other two. This seems like Pythagorean theorem is going to be in order here. And then lastly, probably the easiest one to identify, 4.8% of what length is 17 inches is pretty clearly a percent application. So we're going to think all the way back to our first application section on percents. But let's take a look at the Vern problem. Okay, so, and again, we worked through at least 3 of these 4 problems, not the Rahul and Claudio one, but we worked through 3 of these already, so these should look pretty familiar. But we might not remember exactly how we solved them, but that's okay. We can, work out the solution again. So Vern sold his Mustang for $60,000. Does it matter that he sold a Mustang? Not really. It matters that he has $60,000 that he wants to invest and that he wants to earn 7% interest per year. He's going to put some of the money in Fund A that earns 3% per year and the rest in Fund B that earns 9% per year. And the question is, how much should he invest in each fund if he wants to earn that 7% interest per year? So the interest desired is 7% of $60,000, or that's $4,200. I know 7 times 6 is 42, and then to get my number of decimal places right, I just think, well, 10% of $60,000 would be 6,000, so this is a little less than 6,000. It's got to be 4,200. It's not going to be $420. It's not going to be $42,000. So that's one quick way to do something like this. And his actual, well, the actual interest that he'll earn is what? It's going to, let's say that he puts $A in Fund A and that he puts B dollars, and it's not letting me write that next to that. It's giving me this goofy little cursor thing, but he puts B dollars in Fund B. So the actual amount of interest he'll earn per year is 0.03 times the amount he puts in Fund A plus 0.09 times the amount he puts in fund B. And he wants these to be equal to one another. So I have 0.03 A plus 0.09 B equals 4,200. Now here I have one equation with two variables. I don't think I can get a unique solution here. There are lots of different choices for A and B that could satisfy this. I need to look back to the context of the problem and see, is there a piece of information I haven't used yet? Is there an extra constraint that I can use? Well, he wants to invest the full $60,000 and no more, right? So he can't invest, $50,000 in fund A and $60,000 in fund B. He also doesn't want to invest 10,000 in fund A and 10,000 in fund B. He wants A plus B, the sum of the two amounts invested, to equal 60,000. Or in other words, we could say maybe A equals 60,000 minus B. So the amount he's going to put in fund A is 60,000, what he starts with, minus however much he puts in fund B. And we can plug 60,000 minus B in up here. So in light of this new constraint, I have 0.03 times 60,000 minus B plus 0.09 B equals 4,200. And now it looks like I have one linear equation in one variable, and I should be able to solve this for B and then figure out A. So let's do that. Well, the first thing I want to do is to distribute and simplify. I do have some decimals here, and you might say, well, can I multiply by 100 on both sides to get rid of this 0.03 and this 0.09? I suppose I could, but then I have like 420000, like 4.2 million on the right side. That seems to be unwieldy also. So I don't really see so much benefit in multiplying both sides by 100 and getting rid of the decimals. I think I had mentioned this before when we talked about clearing fractions and clearing decimals, that especially with decimals, sometimes it's worth it and sometimes it's not. And I feel like with decimals, especially, maybe like half the time, it's not even worth it to clear them. So I'm not going to worry about clearing them here. If you wanted to clear them, it's, that's certainly a reasonable choice as well. But we'll distribute. Oh, I forgot an important, I forgot my 60,000 here. Got excited about distributing, and there we go. 0.03 times 60,000 minus 0.03 times B plus 0.09 B equals 4,200. That looks good now. 0.03 times 60,000. Let's see what that gives me on the calculator. That gives me 1,800. I could also have found that by moving this decimal point 2 to the right and this one 2 to the left and done 600 times 3. Then I have 0.09B minus 0.03B is 0.06B, and that's got to equal 4,200. It looks like I've got everything simplified that I can simplify. I want to isolate the variable term now. All right, so 4,200, minus 2,000 would be 2,200, and then plus 200 would be 2,400. And now I want to isolate the variable. So I need B equals 2400 over 0.06. And this says that B equals, well, I can multiply the bottom by 100, shift the decimal point to the right. If I multiply the top by 100, this is 240,000 over 6, or B equals 40,000. Let's check units. Units can be a little tough to check here, but we know that, for instance, this 4,200 is in dollars. The 60,000 is in dollars. So therefore the 1,800, just 0.03 times something in dollars is in dollars. Subtracting two dollar quantities gives me dollars. And then dividing by just a 0.06 that's unitless, that leaves me with a unit of dollars. So that unit looks good. Is the amount that I need to invest kind of like those two vinegar solutions? Is this bigger than 0 and less than 60,000? Yes, it is. If I had said I need to invest negative $20,000 in fund B, that probably doesn't satisfy the question we're asking, right? I mean, I suppose maybe you could say like, well, I could go to the bank and take out a loan for 20,000 or something. I don't know, but that probably wouldn't satisfy the question here. It's a little less egregious than trying to mix negative volume of fluid, but still, because we can kind of go into debt and have negative money, but probably not a solution to the problem. But certainly if I said, if I wanted to invest $80,000 in fund B, we would also balk at that. But 40,000, that is part of 60,000, so that seems like a reasonable answer. And then if I invest 40,000 in fund B, how much is left for fund A? $20,000 will go into fund A. And that also is in dollars. So Vern should invest 40,000 in fund B, 20,000 in fund A in order to invest the full 60,000 at 7% interest. As kind of a side note, this isn't really a math question so much as really kind of a finance or personal finance question. You might say, well, this is kind of silly. If Vern can invest in fund A or fund B, why not just always put all of your money into the fund that earns the higher rate? Why might somebody target a certain rate instead of just investing in the investment that'll get them the highest average return? Any thoughts on that? Is this just some goofy problem that they made up so we can solve some algebra problems? Or is this something that somebody might actually want to do, target a certain interest rate instead of just getting the maximal rate possible?
Aren't higher interest rates like more risky?
Exactly, yeah. So something that's not really mentioned here is fund A at 3% per year. That might be something like a very solid investment, maybe a CD with the bank, certificate of deposit, or maybe in maybe a slightly different interest rate environment, maybe like a treasury bill or something, where it's like, for all intents and purposes, you're guaranteed that 3% per year. There's no ifs, ands, or buts. 9%, I mean, that's a little more like, say, investing in the S&P 500. That's a little more risky, right? If I have something that I'm saving up for and I need 7% interest for that, if I have a retirement account and it needs to throw off a certain amount of money per month to fund my retirement, something like that, if I want to target that 7% interest, I probably don't want to get greedy in some kind of loose sense and put everything into the 9% interest because it's going to be more volatile. It's going to be tougher for me to take out money when the market hits a slump. If I have a mixture of these two funds, number one, when the market hits a slump, I can draw from fund A instead of fund B and let fund B recover. But the other thing is that there's a psychological side to things too. If I'm reliant on my retirement fund and I see that number go down a lot, even if I intellectually know, okay, like the market goes down and recovers, if I see my big number become a lot smaller, like several years salary when I was working, smaller than it was before, that's disconcerting. Even if I intellectually know that, okay, in theory, it's going to come back up and it's come back up every other time that it's gone down, that's not a comfortable feeling. So we can mitigate that a little bit by mixing together less volatile investments with more volatile ones. And on the other hand, we don't want to just say, all right, I'm super scared of everything, I just want to stick my money under the mattress, because, well, earning 3% a year, that's probably not going to fund the retirement that we want to have, right? So that's why you would want a mix of these, practically speaking. So this isn't just, some goofball math problem. This is something that a financial advisor might actually look at and try to figure out what proportion of, investments of low risk versus high risk versus moderate risk do we want in your portfolio to give you the risk profile that you want while still meeting your needs. Okay, so let's go on to the Rahul and Claudia problem. I'll leave the last couple steps of this one up here. I think I can get most of this on one screen here. So just in case you wanted to take a look back at that, there's the last couple of steps of that one, but take about 5 minutes, work on the Rahul and Claudia. And again, if you're going a little quicker than expected, then you can start working on the next ones. But we know this is going to be an inequality problem. So approach this problem with that in mind, with those tools and techniques in mind. We'll take, again, about 5 minutes to work through this one. Okay, so let's take a look at this problem. Let's read through it. Rahul and Claudia decided that to save money, they would move themselves from their apartment to their new house. Pretty much nothing in this initial sentence is important for the mathematics. It just gives some context, just gives a little bit more to the narrative. They had to rent a truck to do this. Also not super relevant, other than just giving some context. Their budget was very strict. They could afford to spend no more than $200. So this is an important piece. No more than pretty strongly suggests we're going to be dealing with an inequality here. So the total cost that's going to be incurred has to be no more than or less than or equal to $200. How does the cost add up? How is the cost calculated? The truck costs $46.50 per day plus 26.5 cents per mile or fraction thereof. So fractional miles, add up at 26.5 cents per mile as well. If they decided they would need the truck for 2 days, so that's an important component that's related to the 46.50. What's the maximum number of full miles? I know that my mileage is charged as 26.5 cents per mile. What's the number of full miles? Maybe I'll call that the variable M, the number of miles they can put on the truck or they can drive the truck. Round your answer down to the nearest whole number. As a kind of a side note, if you're ever running a truck, practically speaking, take into account the whole round trip, not just like from your house to, where you're taking the stuff to or whatever. But you also need to get it from the rental place to your house, pick the stuff up, take it to where you're delivering it to, and then back to the rental place. So those other 2 legs, getting it from the rental place and back to the rental place, you're also paying for those miles. So just be aware of that and take that into consideration. When my wife and I moved, we did a pick up and drop off at 2 different locations because we calculated taking it back to the same location versus paying a little extra to leave it at a closer location. And it was better to leave it at the closer location and let them deal with the logistics of getting it where they need it, than for us to actually drive it back and pay the mileage and the gas and all of that for that extra trip. So sometimes that's something you can do. If the 2 places are far away, you can rent the truck at location A, drive it to your house, transport the stuff, and then drop it off somewhere closer to the area that you're transporting it to, and save the mileage and the gas on the truck. And they typically charge you a little extra to leave it at a different place, but you might save money that way. Anyway, tangential note. Our total cost is the daily cost, $46.50 per day, $46.50. Let me be careful, per day times 2 days. So it's this number of dollars plus mileage cost has to be less than or equal to $200. Mileage cost, though, we got to be really careful here. We might just be tempted to do 26.5 M and then start solving. But 26.5 is actually cents per mile. 26.5 times M gives me cents per mile times number of miles. That actually gives me a unit of cents. That's inconsistent with the other units of dollars in the problem. If I just started here and said, okay, I've got an inequality 46.5 times 2 plus 26.5 M less than or equal to 200, and I solved for M, I'd get a very low number of miles that I could supposedly drive the truck. Because this would, if I just started solving like that, that would be acting like I was paying $26.50 per mile, but that's not actually the case. I need to switch into the proper unit to be consistent with the rest of the units in the other terms in the problem. 26.5 cents is $0.265. So I make that change, 0.265 M, $0.265 per mile times number of miles. Now everything is in units of dollars. Again, units, the context of the problem gives us the units. The units can be used to check and make sure that everything works out right. And in this case, I saw it kind of initially. If I hadn't seen that initially, I would have gotten down and I would have got like, M equals or M less than or equal to 3 or something like that. Like, wait, does it make sense that I could only, I don't know if that's the actual answer, but but you can ask, would that make sense that I could like only drive the truck? I guess it would have been maybe something like more like 6 or 7. Would it make sense that I could only drive the truck 6 or 7 miles for $200 or something along those lines? Probably not. So we would come back and we would say, okay, like something didn't make sense there. Let me check my work. Let me say check my units maybe. And I would identify that I had a units issue here, fix that, and then hopefully get a more reasonable answer. But at this point, everything is in the correct units. I've got an inequality in one variable. I'm going to simplify the stuff I can simplify first, which is multiplying 46.5 times 2. And now I'm ready to go through my equation or inequality solving steps, isolate the variable term. 2000 or 200 minus 93 is 107. And then I want to isolate the variable. I'm going to divide by positive 0.265. The inequality stays the same way. And then I'll come over to my calculator and figure this out. 107 divided by 0.265. This gives me 403.8 or so. And the instruction in the problem tells us round down to the nearest whole number. But by context, we could tell that anyway, because the total cost has to be less than or equal to 200. We want to answer as a whole number. So if we want our answer as a whole number, we need to drive less than or equal to 403 miles. Maybe we're looking at the odometer and it only ticks over in units of whole miles. And, we're trying to plan our trip so that in total we have less than 403 miles, less than or equal to 403 miles. That will keep us within our budget. So again, a couple of pieces of complexity here. It's kind of easy to miss this 2 here because we're running it for 2 days. So we need 2 lots of 4650 accounted for, not just one. And it's very easy to miss this unit. That one of our terms naturally, when we just pull the numbers out, is in cents versus dollars for the others. So if you missed either of those, no big deal. If you missed the 2 days and just did 4650 and didn't have times 2, you actually would probably still get a pretty reasonable number down here. You would get, maybe something like 160 miles more or something like that. 150, 200 miles more. So like somewhere in the ballpark of 600 miles or something. That would actually be pretty reasonable. And it would be really hard to catch an error like that. But if you missed the error in cents and you had basically set up the equation in such a way that it was claiming you were being charged $26 per mile, then you'd have got like 3 or 4 miles is all that you could drive the truck. And pretty clearly that's not going to be a reasonable answer. Some mistakes, are easy to catch with kind of reasonability checks. Some mistakes are, a little more insidious and are going to be harder to catch. So that's just kind of the nature of these kinds of problems. Okay. So let's look at these next 2, and maybe we'll take 5 minutes and just go through both of the next 2. So I'll give you 5 minutes to work through them both, and then we'll come back and we'll just work through them both. These 2 are, I think, a level down in difficulty from the previous ones. Okay, so let's look at the answers to these two problems. So the first one, we had kind of previously identified this as a geometry problem. Seemed like it dealt with a triangle, specifically a right triangle, because hopefully at least the walls of the house are perpendicular to the ground. And we see we have a 10-meter extension ladder. So the ladder is going to be leaned against the house. The base of the ladder is going to be 6 meters away from the house. The ladder is 10 meters long. And we want to know how many meters up the side of the house will the top of the ladder reach. We'll call that H for height. We see we can model this situation as a right triangle with side lengths H and 6 and hypotenuse 10. And then I see the Pythagorean theorem says that H squared plus 6 squared equals 10 squared, or H squared plus 36 equals 100. And again, if I see this, I might, naturally think to myself, wait, we've talked about solving linear equations, but not quadratic equations, not equations where the variable is squared. How am I going to solve this? But again, one of the really powerful ideas in math is that we can take patterns that we've used to solve certain problems, and we can ask, can I adapt that pattern? Can I follow kind of the same abstract process and maybe work my way towards a solution for a slightly different type of problem? I still have variable terms and constant terms. Can I isolate the variable term? Well, sure, I can subtract 36 from both sides and get H squared equals 64. And now can I solve this? Well, I can basically solve it just by general knowledge, just by knowing my squares and my times tables. I know that 8 squared is 64. So in this case, the height up the wall is going to be 8 meters. He'll be able to lean the ladder and it will touch 8 meters up the wall. Now, if he wants to know how high he can paint, he'll have to also know like how tall he is, how many rungs from the top of the ladder he is willing to stand, how far his reach is, and so on. So this isn't exactly saying how high up the wall he'll be able to paint, but this is at least a start. Any questions on that problem? Okay, and the next problem, for the percent problem, we identified this as a percent application. 4.8% of what length is 17 inches. We know of and is often means times and equals. What length is what we're looking for. Maybe I'll give it the variable name L. So 4.8% times L equals 17. I know that 17 is in units of inches. 4.8% is a unitless quantity. So L should be in inches. The length should be in inches. If I change this 4.8% into a decimal, 0.048 times L equals 17, and then I divide by 0.048, I see that on the right side here, I have 17 inches divided by the unitless 0.048. I do 17 over 0.048 in the calculator, and that gives me about 354.17. And inches over a unitless quantity gives me inches, as I would expect for my lane. Okay. Does that seem pretty reasonable? I need a small percentage of this to be 17 inches. Yeah, a small percentage of a few hundred might be in the ballpark of 17 inches. That seems pretty reasonable. Are there any questions on anything we covered today? Okay, so again, what we talked about today was solving applications with inequalities. One of the challenging things with inequalities is that we often don't have a quote is to set the equals. We might have to use a little bit more context from the problem. So I think that's one of the more challenging things is you just have to read the problem very carefully, be really careful about the way that the problem statement gives the information, is it at least or no more than? Do you want a strict inequality or not? That might come into play. Be careful with what the rounding is going to look like. In this case, the number 40.8, when we round to the quote nearest whole number, it happens to round to 41. But note also, if we had gotten, 40.3, we would have still rounded up to 41. So we have to round in the correct direction to satisfy the context. We can use units, we can use common sense in a sense to check, she's not going to need to sell 1,000 aprons, or she can't sell a negative number of aprons. We can use that to check our answers. And then also, like in the practice here, now that we've built up, some foundational material and some additional tools and techniques with some different formulas and so on, sometimes half the battle is figuring out what formulas are likely to apply, what tools and techniques are likely to be helpful. And sometimes, just identifying what kind of problem and what tools and techniques you might expect to see here, sometimes that can give you a step in the right direction. Right? The more, in a sense, tools we throw into the toolbox as we go through the course, the more structure that we need to build in initially to sort through and say, okay, these ones are probably not going to be helpful here. Like I equals PRT isn't really helpful here, but maybe something dealing with geometry is going to be helpful because we have, a bunch of straight lines. A bunch of straight lines makes me think of geometry and triangles or rectangles or something like that. So I think that is about what I wanted to get through today. Unless there are any questions, we will end it here.